Hello everyone, thank you for coming. My name is Chris Davies and I'm a postdoc at LMU in Munich, and today I will be talking about how we can do cosmology with weak lensing voids and weak lensing peaks. So first of all, just a quick reminder about weak gravitational lensing. So on the top left here we have a distant source galaxy, and that source galaxy will emit light along the line of sight towards the observer. As this light travels towards the observer, its path will be perturbed by intervening gravitational potentials along the line of sight. And this results in the observer seeing a distorted version of the source galaxy image. We can quantify this distortion with two parameters, the first of which is convergence, kappa. Kappa, its positive and negative values, tell us how magnified or demagnified the image is. And shear, gamma, the second parameter, is a complex number, and its real and imaginary components tell us along which axis the image is stretched. So, that's weak lensing. What are some of the useful things that we can do in the weak lensing convergence field? So, we have a colour map in the middle here, which corresponds to the convergence or the simulated convergence measured in patches of the sky, where bright colours correspond to high convergence and dark colours correspond to low convergence. What we're interested in here is looking at how we can extract information from this convergence field, mostly in the form of peak statistics and useful things that we can do with those peaks, where here I have overplotted peaks in the convergence field, local maxima as green dots on top of this colour map. We know that high amplitude peaks correspond to clusters along the line of sight, clusters of galaxies. And we also know that low amplitude peaks correspond to chance alignments of low mass halos along the line of sight. And it is these features that makes weak lensing peaks a useful cosmological probe of the universe. On the bottom left here I have an image of a fiducial simulated lambda CDM peak abundance, which is one of the statistics we're interested in here, which tells us how many peaks we have as a function of their peak amplitude, nu, where nu is a rescaled definition of the convergence, which is essentially a signal to noise quantity, which is just the rescaled convergence. On the right we have some parameter constraints from real observational data, which has come from DES year 3. Here, these posteriors correspond to constraints from peaks, weak lensing peaks in green, and the 3 by 2 point correlation functions in the grey dashed lines. What you can see here is that the peak constraints are able to chop off or rule out the bottom third of the 3 by 2 point correlation function contours. This is telling us that by including peak information, we are able to further improve our cosmology constraints compared to the standard approach. So the question that I'm interested in for the rest of this talk is what else can we do with weak lensing peaks? Now, on the left, we could just continue measuring peak statistics. So we have the peak abundance, which is well established, and something that I will also be talking about is measuring the peak 2-point correlation function, which tells us how clustered the weak lensing peaks are and what cosmology information there is there. On the right, we could also use peaks to find voids. And in this case, we're looking at a new class of void, weak lensing voids, which are 2D underdensities identified in the convergence field, where we use peaks as tracers for these void finding algorithms. And with these voids, we can define two more new and useful statistics to probe cosmology: the void abundance, so how many voids we have as a function of their size, and the void lensing profiles, which is a proxy for the matter distribution within those voids, or the average matter distribution within the stacked voids. So, the first steps that we make for our higher order peak analysis is as follows. We measure all local maxima in the convergence field, which is exemplified by these green dots on these colour maps, and once we have identified all weak lensing peaks, we then impose a height cut, where we remove all peaks below a given new threshold. So on the left panel here, I have removed all peaks with an amplitude lower than a signal to noise of 1, and on the far right I have removed all peaks that have a signal to noise amplitude that is less than 4. For each of these catalogues then we can measure how the peaks are clustered. You can see that on the left the peaks for the new larger than 1 catalogue appear to be more randomly distributed, and on the right they appear to be more clustered. So you can see that the clustering will change through the different peak catalogues. On the bottom row we then also use these different peak catalogues to find different void populations. So we put each catalogue into a void finding algorithm which gives us different void catalogues, and you can see here how the void populations differ between different catalogues, and we will see why this is useful later on, where the voids here are the white circles plotted on top of the green dots in the bottom row. So we've just defined a new type of void, and it is also interesting to see how weak lensing voids compare to galaxy voids. This plot on the right is a comparison between the simulated weak lensing void lensing profiles in colour and the simulated galaxy void weak lensing profiles in black. You can see that weak lensing voids have deeper lensing profiles compared to galaxy voids, which is telling us that weak lensing voids correspond to deeper underdensities along the line of sight. So weak lensing voids are emptier than galaxy voids. An additional advantage is that the convergence field is closely linked to the dark matter field. This means that when we're looking at weak lensing voids, we do not have to worry about the galaxy halo connection, which is something that we are worried about when we're looking at galaxy voids. So, next we can see how these 4 statistics that we're interested in, we can see how they behave as a function of this new threshold, or how the statistics change from one peak catalogue to the next. So on the top left here we have the peak abundance, and it is within the peak abundance that we are making these new cuts. So the peak abundance is just constant here. On the bottom left we have the peak 2-point correlation function as measured for each of these peak catalogues. And you can see that as the new threshold increases between catalogues, the amplitude of the peak 2-point correlation function also increases, which is telling us that higher new threshold catalogues contain more clustered peaks. On the top right, we are looking at the void abundance as a function of this new threshold, where we see that the largest voids are in the highest new threshold catalogues, and the smallest voids are in the lowest new threshold catalogues. This is similar to what we saw on the previous slide here. Okay, and for the void profiles on the bottom right, we see that the deepest profiles come from the smallest new threshold catalogue, and the sharpest profiles come from the highest new threshold catalogue, where the sharpness here is just how quickly the void profile peaks at the void boundary. So you can see that there's a broad peak in the blue curve and a narrower peak, or a sharper peak, in the red curve on the bottom right here. So that is what our statistics are, how we measure them, and how they vary, or how they behave in an isolated environment for a fixed cosmology. Now we want to use these new statistics that we've made to actually constrain or forecast constraints for some cosmological parameters. To do this, we use the cosmosLICS simulations, which has 26 nodes in a 4D wCDM parameter space, where we vary omega n, S8, H, and W0. For each of these nodes, we have 50 weak lensing convergence maps, which are ray traced from n-body simulations, and they match the Rubin n of z. Each map is 10 by 10 degrees squared, and we have also suppressed cosmic variance in this sample. We also have 615 realizations at a fiducial lambda CDM cosmology, shown by the black star in this Latin hypercube on the right, which we use for covariance estimation. So for each of these nodes, we are able to measure average statistics, average peak abundances, average peak clusterings, average void abundances, and average void profiles. And we can use these measurements to train a Gaussian process emulator. With that emulator, we can then learn about how these statistics depend on these 4 cosmological parameters, and we can use that machinery to create posterior forecasts for a stage 4 survey. So, once we have measured our statistics in the cosmosLICS suite, we plug those measurements into a Gaussian process emulator and use the emulator to learn about how the statistics depend on each of these cosmological parameters. So on the top left here, for the peak abundance, in each of these panels we are varying only one cosmological parameter at a time and keeping the other three held constant. So on the left, for the peak abundance, we only vary omega m in panel A, and then in panel B we only vary S8, in C we only vary H, and in D we only vary W0. For the peak abundance, you can see that most of the dependence on cosmology is coming from omega m and S8, with a small dependence on H and W0 in these panels, where both the high abundance of high amplitude peaks and low amplitude peaks appears to be sensitive to the cosmological parameters. So it is not just the high amplitude peaks that have useful cosmological information. On the right, we have the peak 2-point correlation function, and we see here that the peak clustering seems to depend most strongly on omega m, with then a similar dependence on S8, H and W0, where they vary less strongly than omega m, but all similarly amongst themselves. On the bottom row, we have how the void statistics depend on these four cosmological parameters, where we can see in the far left that the void abundance seems to depend most strongly on omega m, and somewhat strongly on S8, with hardly any dependence on H and W0. And for the void lensing profiles on the right, on the bottom right, we see that the strongest dependence on a cosmological parameter is for S8, with moderate dependence on W0 and omega m, and hardly any dependence on H relative to the error bars. We also see that for the void lensing profiles, most of the cosmology dependence is happening at the void boundary, where R over RV is equal to 1. Okay, so that is how our statistics depend on the cosmological parameters. Now we can use this machinery to actually forecast some parameter constraints. On the left, we have the forecast constraints on these four parameters from the peak clustering, where we have 4 contours in colour, where each contour corresponds to the constraints from an individual catalogue. So an individual 2-point correlation function measurement from one catalogue. You can see that as the new threshold increases, the shape and orientation of these catalogue changes, of these contours changes between catalogues. This tells us that the clustering of different catalogues contains different cosmological information. So when we combine the constraints from these 4 2-point correlation function measurements, one for each of the catalogues we're looking at, we actually end up with significantly improved parameter constraints, which we can see in the black contour here, thanks to the complementary degeneracy between different catalogues, the clustering of different catalogues. Now on the right, we are comparing the peak abundance in blue to the peak clustering in orange, where we're comparing their constraining power here. What you can see is that the peak abundance seems to give tighter constraints in the omega m S8 plane, where the blue contour is narrower than the orange contour. However, the peak clustering seems to be dominating the constraints in the W0 H plane, where you can see that the orange contour is significantly smaller than the blue contour, telling us that peak clustering offers a lot of extra complementary information compared to the peak abundance alone. And similarly, you can see how combining the two gives us these green contours, constraints from abundance plus clustering, which is significantly tighter than any one of them on their own. Again, we do a similar thing for the void statistics, where we have constraints from the void abundance for 3 catalogues on the left and the void profiles for 3 catalogues on the right. Again, for the void abundance on the left, you can see that the different catalogues have the contours for the different catalogues have different shapes and orientations. So again, we get a significant improvement when we combine constraints from each catalogue. For the lensing profiles, the contours appear to be less complementary to each other. So when we make a combination of all of these statistics, all of these catalogues, we get less significant improvements. So Next, we make a comparison between the constraints from the void statistics and the peak statistics, where the void constraints include abundance plus lensing profiles for all catalogues, and the peak statistics include abundance plus clustering for all peak catalogues. And you can see here that both peaks and voids give tighter constraints on their own for S8 and W0 compared to the standard shear 2-point correlation function measurement, which is shown by the grey contour. We see that the voids give slightly tighter constraints for omega m than the peaks, and the peaks give slightly tighter constraints for S8 than the voids. We also see that the shear 2-point correlation function is better than both the peaks and the voids at constraining h, the Hubble parameter. And finally, we see from the green contour, when we combine the constraints from the peaks and the voids, that the constraints are tighter than the shear 2-point correlation function for all parameters. So this is really telling us that going to these higher order statistics is allowing us to extract a lot more cosmological information. Finally, we have some additional simulations that allow us some additional suites of n-body simulations that allow us to test how these statistics depend on two modified gravity models, nDGP in the top and f of r gravity in the bottom. So now we can vary these modified gravity parameters and see how these statistics change. Just as a reminder, in these modified gravity models, we are introducing an additional gravity-like fifth force which enhances structure formation in certain regimes. On the left here, we see that the abundance of the peaks is sensitive to modified gravity, mostly at the high convergence end, but also at the negative convergence regime. And on the right, we also see that the clustering of weak lensing peaks is not only sensitive to modified gravity, but it is sensitive to different modified gravity models, where you see that in nDGP, the clustering of peaks is enhanced, but in f of r, the clustering of peaks is dampened. So this is useful because not only will we be able to constrain the strength of modified gravity, we may also be able to distinguish between different models. Finally, this is how the void statistics vary with modified gravity, where again, for the void abundance, you can see that the large radius voids appear to be sensitive to different modified gravity models, and for the lensing profiles on the right, there is strong enhancement at the void boundary for these different modified gravity models. So I will just leave my conclusions here to be read. Thank you everybody for listening.